4 humans are flying past the moon right now, today, April 6, 2026. They are closer to the lunar surface than any person has been in over 50 years, and they will not land. The most powerful rocket ever built carried them there. A spacecraft designed specifically for the moon is carrying them around it, and yet they are flying straight past. We're going to find out exactly why. The crumbling heat shield NASA cannot explain. The missing lander, the steepest reentry in human history. The far side of the moon that human eyes are seeing for the first time ever, right now. If this grips you the way it grips us, subscribe and stay close. Prepare yourselves. We begin. Right now, 4 human beings are closer to the moon than any person has been since December of 1972. They launched on April 1st, 2026. They rode the most powerful rocket NASA has ever successfully flown with a crew aboard. They crossed the invisible line where the moon's gravity pulls harder than Earth's. They pressed their faces to the windows and saw craters that no human eye had ever directly observed. And in a few hours they will swing around the far side of the moon, lose all contact with Earth, and ride gravity home. They will not set foot on the surface. They will not even slow down enough to enter lunar orbit. That is the part nobody expected to still be true in 2026. When the Artemis program launched its first uncrewed test flight back in 2022, the plan felt straightforward. Test the rocket, test the capsule with no crew, then fly humans around the moon. Then land. The whole world watched the Space Launch System lift off from Florida and felt something shift. Humanity was going back. The timeline said astronauts would be on the lunar surface by 2025, then 2027, then, quietly, 2028. Every delay had a reason, and those reasons, stacked on top of each other, reveal something important about how hard this actually is. Artemis 2, the mission currently underway, carries 4 astronauts. Reed Wiseman, the commander, a veteran of the International Space Station, who is now the oldest person ever to travel beyond low Earth orbit. Victor Glover, the pilot, who became the first person of color to travel this far from Earth the moment Orion left our planet's gravitational neighborhood. Christina Koch, mission specialist, the first woman to journey beyond low Earth orbit in all of human history. And Jeremy Hansen, a Canadian Space Agency astronaut and the first non-American ever to fly near the moon, placed on this crew through a formal treaty between the United States and Canada. 4 firsts on a single spacecraft. A capsule orbiting nothing, touching nothing, landing nowhere. That tension is worth sitting with. Because the reason this mission exists exactly as it does, flying a loop around the moon and coming straight home, is rooted in a problem that emerged on the very first Artemis test. A problem NASA discovered after the fact. A problem the agency still does not fully understand. The mission right now is already breaking records. The crew is traveling a maximum distance of 2,757 miles from Earth. That beats a record set over 50 years ago, under the worst possible circumstances, by a crew that almost did not come home at all. That record, and the tragic mission that set it, turn out to be deeply connected to why Artemis 2 is flying the exact same trajectory today. The crew is already returning science. They are photographing lunar geology, observing color shifts across the surface that could answer a mystery about how the moon formed 2 hemispheres that look nothing like each other. They are running medical experiments. They are testing communication systems that could one day reach Mars. And they are proving, one data point at a time, that the Orion spacecraft can keep human beings alive in deep space. Because before anyone lands on the moon, someone has to survive getting there and back. That sounds obvious. It is surprisingly hard to guarantee there is something quietly extraordinary about what today represents. The last humans to see the moon this close were the crew of Apollo 17. They splashed down on December 19, 1972. Every person alive today who was not yet born on that date has lived their entire life in a world where no human went back. That 50-year gap has an explanation, and the explanation is darker and more complicated than most people know. But before we get there, we need to talk about what almost stopped Artemis 2 from launching at all. A shield. a burn, and a discovery that forced NASA to tear up its re-entry plan from scratch. The Artemis 1 mission should have been a triumph, and by most measures it was. The Space Launch System rocket lifts off in the dark from Kennedy Space Center in Florida. No crew aboard, just an uncrewed Orion capsule loaded with sensors, dummies, and radiation detectors. The mission runs for 25.5 days. Orion loops around the moon, enters a distant retrograde orbit farther from Earth than any spacecraft built for human use had ever traveled, and begins the long fall home. Then it hits the atmosphere. Orion re-enters at roughly 25,000 miles per hour. That speed generates temperatures on the heat shield face that approach 5,000 degrees Fahrenheit. The shield is made of a material called avcoat, a foam-filled honeycomb designed to ablate, meaning it is supposed to burn away in a controlled, predictable manner, sacrificing itself layer by layer to protect the capsule behind it. The engineers watching the data expected a certain amount of material loss. What they saw was something different. Chunks of the shield had fallen away in ways the computer models did not predict. The ablation was uneven. Sections that should have held had eroded faster, and in patterns that did not match any simulation run before the flight. A few of those chunks, tumbling free during re-entry, flew close enough to the capsule's windows to be captured on camera. Nobody was aboard. Nobody was hurt. The capsule splashed down safely. But the engineers who reviewed the footage and the recovered hardware understood immediately that they had a serious problem. The heat shield on Artemis I used a skip re-entry profile. Picture a stone skipping across water. Orion was designed to briefly dip into the upper atmosphere, use the lift generated by its shape to bounce back outward slightly, dissipate a portion of its entry heat on that first pass, then come back down for the final plunge. That two-stage approach was supposed to reduce peak temperatures, improve landing precision, and make the whole experience gentler on both the spacecraft and any crew inside. After what they saw on Artemis I, mission managers made a decision that changed the entire Artemis 2 flight plan. They eliminated the skip re-entry entirely. The new plan sends Orion straight in. One pass. No bounce, a steeper angle, higher peak temperatures, and the fastest crewed re-entry ever attempted in the history of human spaceflight. 2,000 miles of outbound travel, and then a controlled fall through fire at 25,000 miles per hour, with no second chance to course correct. The reason they made this trade is important. A skip re-entry requires precision. It requires the heat shield to perform exactly as predicted on the first atmospheric pass, because that first pass determines the angle and energy of everything that follows. If the shield erodes unevenly on that initial dip, the behavior on the second plunge becomes unpredictable. Engineers could not certify that outcome as safe for a crew. A steeper direct entry is more brutal, but it is more predictable. One pass, one load, one known profile. The shield takes more heat all at once, but the engineers can model that scenario with higher confidence. The honest reality, confirmed by NASA, is that the agency still does not fully understand why the Artemis 1 shield eroded the way it did. Investigations identified several contributing factors, including manufacturing variations in the avcoat fill and unexpected airflow behavior during re-entry. But a complete mechanistic explanation, the kind that lets engineers say with certainty they have fixed the root cause, has not been publicly declared. What they have done instead is remove the scenario most sensitive to shield performance. Strip out the skip, fly straighter, accept the violence of direct entry as the safer of two uncertain options. The crew of Artemis 2 will re-enter Earth's atmosphere on approximately April 10th. At that moment, they will be moving faster than any crewed spacecraft has moved during re-entry in the history of spaceflight. And they will do it with a heat shield whose full behavior under those conditions has never been tested with humans aboard. The data from that re-entry will determine whether Artemis 3 can proceed at all. But there is another reason Artemis 2 cannot land, one that has nothing to do with the heat shield, one that was always built into the plan. And it comes down to a problem nobody talks about plainly enough. There is no lander. Getting to the moon and landing on the moon are two completely separate problems. This surprises people. The Saturn V rocket that carried the Apollo astronauts looked like one machine, a single towering vehicle pointed straight up. But inside it were multiple spacecraft, each designed for a completely different job. The command module brought the crew to lunar orbit and brought them home. The lunar module was a separate vehicle entirely, a spidery, angular craft that only existed to go from orbit down to the surface and back up again. The lunar module never touched Earth. It was too fragile. Its legs were designed for 1/6 of Earth's gravity. Its skin was so thin that engineers have described it as similar in thickness to a few layers of aluminum foil in places. It was built entirely for the moon. Artemis has the equivalent of the command module. Orion is that spacecraft. It can carry 4 astronauts from Earth to the moon's vicinity and return them safely. It is what is flying right now. What Artemis does not yet have, certified and ready for a crewed lunar landing, is the lunar module equivalent. NASA awarded contracts for a human landing system to 2 companies. SpaceX won the first contract in 2021 to develop a crewed lunar lander derived from its Starship vehicle. Blue Origin, the company founded by Jeff Bezos, won a second contract in 2023 for a competing lander called Blue Moon. Both vehicles are enormous. SpaceX's Starship is the largest rocket ever built, standing nearly 400 feet tall in its full configuration. Blue Moon is smaller, but still a major spacecraft. Both are still in active development and testing as of this mission. The plan for Artemis 3, currently targeted for 2028, works like this. Orion carries the crew to lunar orbit. A lander, either Starship or Blue Moon, is already waiting there, having been sent ahead on a separate uncrewed launch. The Orion crew transfers into the lander through a docking port. The lander descends to the surface. The crew walks on the moon. The lander ascends, docks again with the waiting Orion. The crew transfers back, and Orion brings them home to Earth. Every single step of that sequence requires a piece of hardware that has never performed that exact function before, in that exact environment, with human lives depending on it. The docking in lunar orbit has never been tested at lunar distance with a crewed vehicle. The lander descent has never been performed with a crew. The ascent from the moon has not been tested at all by either of the current vehicles. And the rendezvous in lunar orbit, after ascent, finding and docking with Orion after launching off the lunar surface, is one of the most technically demanding operations in spaceflight history. Apollo did all of this, but Apollo had a purpose-built lunar module that had been tested on multiple missions before astronauts rode it to the surface. The first crewed lunar module flight was Apollo 9 in Earth orbit. The first flight to the moon's vicinity was Apollo 10, which descended to within 50,000 feet of the surface before pulling back. Only then, on Apollo 11, did astronauts land. Artemis 3 currently plans to land on its first attempt. That is what makes Artemis 2 so critical. It is not a placeholder mission. Every system check the crew runs, every manual piloting test, every medical data point, every piece of re-entry telemetry feeds directly into the question of whether Artemis 3 is ready to attempt what Apollo only reached after years of incremental steps. 4 humans are flying past the moon today because the moon itself is waiting for something that is not ready yet. And the story of why it took so long to get even this far goes deeper than most realize. Apollo 17 lifted off from the lunar surface on December 14, 1972. Commander Gene Cernan was the last person to step off the moon. His final words before climbing the ladder were spoken quietly, more to himself than to mission control. He said he was certain humanity would return. He was wrong about the timeline by at least 54 years. And counting, no human being went back. And the reason why is one of the most revealing stories in the history of exploration. The Apollo program did not end because the missions failed. It ended because they succeeded too well, too fast, and for reasons that had little to do with science. Apollo was born inside the Cold War. The United States and the Soviet Union were not competing to advance human knowledge. They were competing to demonstrate which political system could project the greater technological power. When President Kennedy stood before Congress in 1961 and challenged the nation to reach the moon before the decade ended, he was responding to the Soviet Union launching a man into orbit just weeks earlier. The moon was a flag, The first flag planted there would belong to the winning ideology. Apollo 11 landed in July of 1969. The flag was planted. The race was won. From that moment, the political logic that had funded Apollo began to dissolve. Each subsequent mission cost roughly the equivalent of several $100 million in today's money. The Vietnam War was consuming the federal budget. Public attention, briefly transfixed by the achievement, moved on. Congress began cutting NASA's budget almost immediately after the first landing. 3 planned Apollo missions were cancelled. Apollos 18, 19, and 20 never flew. Hardware that had already been built sat in warehouses. One Saturn V rocket ended up as a lawn ornament outside NASA's Johnson Space Center in Houston, never launched. The space shuttle program that followed was designed for low Earth orbit. It was never intended to go beyond it. For 30 years, from 1981 to 2011, NASA's human spaceflight program circled Earth at roughly 250 miles altitude, never venturing farther. After the shuttle retired, the United States had no vehicle of its own capable of reaching even the International Space Station. American astronauts rode Russian rockets for 9 years. The Artemis program formally began in 2017. Its stated goal was to return humans to the moon by 2024. Political pressure, budget realities, technical challenges, and the heat shield problem pushed that date back by at least 4 years for a flyby, and farther still for a landing. So the 50-year gap between Apollo 17 and Artemis 2 represents something specific. What happens when exploration is funded as a competition rather than a commitment? The technology to return existed for decades. The sustained will to use it did not. The crew currently flying past the moon is the first generation of astronauts to go beyond low Earth orbit since the final Apollo crew splashed down. They are also flying a trajectory that carries the specific echo of the most famous survival story in NASA history. A trajectory so carefully designed that it requires no engine to bring the crew home. Only gravity, time, and physics. That design choice was not obvious, and the mission that proved it could work almost killed everyone aboard. Imagine throwing a ball in a perfectly curved arc over a wall and having it curve back to your hand without touching anything. You throw it with enough energy to clear the wall, but not enough to escape. The wall's presence changes the path. The ball swings around and comes home. That is, in simplified form, what Artemis 2 is doing right now. The technical name is a free return trajectory. Orion was placed on a precise path after leaving Earth orbit, such that the moon's gravity will bend its course around the far side and sling it back toward Earth. No additional engine burn required. No active maneuver needed. If every system on the spacecraft failed at this moment, if the engines went silent, if mission control lost all contact, the crew would still return to Earth on this path. That guarantee is not an accident. It is a design choice made specifically because of what happened to Apollo 13. In April of 1970, the Apollo 13 spacecraft was 56 hours into its flight to the moon when an oxygen tank in the service module exploded. The explosion destroyed the fuel cells that generated electricity for the command module. Without power, the crew could not fire the main engine. Without the main engine, a normal abort was impossible. What saved them was the trajectory. Apollo 13 was on a free return path. The moon's gravity did the work. The crew survived by retreating into the lunar module, using it as a lifeboat, and riding the natural curve of the trajectory back to Earth over 4 days. They traveled farther from Earth than any humans in history at that point, reaching roughly 248,000 miles at their maximum distance, a record that stood for over 50 years. Artemis 2 has now surpassed it. The Orion spacecraft carrying Wiseman, Glover, Koch, and Hansen reached a maximum distance of 252,757 miles from Earth during this mission, confirmed by NASA, a new record, set not in a crisis, but deliberately. The free return trajectory carries real constraints. A spacecraft on this path cannot enter lunar orbit. Entering orbit requires slowing down, and slowing down means burning an engine, which means you are no longer on a purely gravitational return path. Artemis 2 made a deliberate choice to stay on the free return arc, keeping the safety of automatic Earth return as a non-negotiable feature of this first crewed deep space test. That choice costs something. The mission cannot orbit the moon. It cannot hover over specific locations for extended observation. It cannot deploy anything to the surface. The lunar flyby is a swing, not a stop, passing within approximately 4,000 miles of the surface at closest approach before the path curves back. 4,000 miles sounds like a large gap, relative to the moon's diameter of about 2,159 miles. The spacecraft passes at roughly twice the moon's own width above its surface. Still, at that distance, the moon fills the windows of the Orion capsule like a wall, appearing about the size of a basketball held at arm's length. The crew described their reaction to mission control in terms that suggested professional detachment was proving difficult to maintain. Commander Wiseman radioed that all four of them had looked at the moon their entire lives and were responding to what they saw out the window, like children. Scientists on the ground were glad for that reaction. The crew has specific scientific observation assignments during the flyby: geological targets, color mapping, crater documentation. Their eyes and cameras are science instruments, but the trajectory also gives them something no Apollo crew ever had: a view of the lunar far side under specific lighting conditions that no crewed mission has captured before. What they are seeing raises a question that has puzzled scientists since the first photographs of the far side came back in 1959. The two faces of the moon look like they belong to different worlds entirely. The near side of the moon is the face you have seen your entire life. It has the dark patches ancient cultures mistook for seas. It has relatively flat plains, a thin crust, and heavy evidence of ancient volcanic activity. Lava once flooded its low-lying regions, filling impact basins and creating the smooth, dark expanses visible from Earth on any clear night. The far side looks like a completely different object. It has a much thicker crust, in places nearly twice as thick as the near side. Its terrain sits higher, more mountainous, more heavily cratered. The volcanic history that shaped the near side barely touched it. There are far fewer of those dark, smooth plains. The surface is rougher, older looking, scarred primarily by impacts rather than shaped by internal heat. Scientists have known about this asymmetry since the Soviet Lunar 3 spacecraft photographed the far side for the first time in 1959. They have debated its cause for 66 years. Several competing theories exist, and none has been decisively confirmed. One theory holds that the moon formed with two separate moons that later merged, the smaller one contributing the thick highland crust now covering the far side. Another theory involves the early Earth radiating so much heat toward the moon, when both bodies were young, that it kept the near side's interior molten longer, driving volcanic activity there, while the far side cooled and solidified. A third theory involves the gravitational interaction between the moon and Earth, creating asymmetric tidal heating over billions of years. None of these is settled science. All of them are active research areas. The Artemis 2 crew is observing the far side right now under illumination conditions no crewed mission has previously captured. Apollo missions launched into windows where the near side was sunlit, because that is where they needed to land. The far side was in darkness during those flybys, limiting what could be photographed. Artemis 2's flight window places the far side in partial illumination, with sunlight striking at low angles that create long shadows stretching across craters and ridges. Low-angle light is a geologist's tool. When light falls flat across a surface, it reveals texture that direct overhead illumination hides. Shadow edges trace ridgelines, crater rims, and slope gradients with precision that satellite imaging from orbit can approximate, but human eyes with handheld cameras at close range can refine further. The crew trained for this specifically, using a sand experiment during preparation, where they adjusted light angles to identify texture and composition clues invisible under flat lighting. What they are photographing could help distinguish between the competing theories. The distribution and depth of impact craters on the far side, compared to the near side visible under similar lighting, could show whether the two hemispheres experienced different bombardment histories, which would support the two-moon merger theory. Color variations across the surface can hint at compositional differences, telling scientists whether the thick far side crust is made of fundamentally different material, or just more of the same material stacked thicker. And within the far side, one feature stands out as particularly significant. A feature so large it should not exist in a visible form. Yet the crew is photographing it, right now from a position no human has occupied before, the Orientale Basin. A scar so old and so massive that understanding it may rewrite the early history of the entire inner solar system. About 3.8 billion years ago, something hit the moon. The object was probably roughly 60 miles across. It was moving at tens of thousands of miles per hour. When it struck, it released energy equivalent to hundreds of millions of nuclear weapons detonating simultaneously. The impact punched through the lunar crust, sent molten rock spraying across a vast area, and carved a hole so deep and wide that the moon's interior partially collapsed inward to fill it. What remained is the Orientale Basin, a circular scar approximately 580 miles across, ringed by 3 concentric mountain ridges that rise as high as 20,000 feet above the basin floor. From above, the feature looks like a bullseye stamped into the moon's surface by something incomprehensibly violent. From Earth, you cannot see it properly. Orientale sits right on the western edge of the moon's near side, at an angle so extreme that it appears as a barely visible ripple when conditions are right. For most of recorded history, humans looking up at the moon had no idea this feature existed at all. It was mapped from orbit and photographed by spacecraft, but no human crew had ever been in a position to see it directly with their own eyes until today. The Artemis II crew photographed Orientale during their approach. Koch described the view from the window as absolutely phenomenal. Mission controllers confirmed the crew captured the basin under the oblique lighting conditions scientists requested. Why does this matter beyond the visual spectacle? Because Orientale is unusually well preserved. Most large impact basins on the moon and in the inner solar system generally have been modified over billions of years by subsequent impacts, volcanic flooding, and slow geological creep. Orientale formed near the end of the period of intense bombardment that struck all the rocky planets and moons, roughly 3.8 to 4 billion years ago, a period scientists call the Late Heavy Bombardment. Because it formed late in that period, and because the far side had less volcanic activity afterward to flood and erase its features, Orientale's structure survived in something close to its original form. Studying the basin's rings, depth, and composition gives scientists a direct window into how large impacts shaped the early solar system. The spacing and height of those concentric mountain ridges tells researchers how deep the initial crater was before collapse, which in turn tells them about the physical properties of the lunar crust at the time of impact. Data from the Artemis II crew's photographs and observations will be combined with orbital datasets collected by satellites over the past decade. Human eyes at close range notice things automated cameras miss: unexpected color shifts, surface textures that suggest different rock types, shadow patterns that reveal hidden topography. The crew's observations are a science instrument that cannot be replicated by a satellite. But the Orientale Basin is just one piece of a larger geological story the crew is documenting today. And while the moon's ancient wounds reveal its past, what lies on the surface right now, in the places Artemis III will eventually target, is something far more immediately important for the future of human exploration. Something that should not be there, according to everything scientists once assumed about the moon. Frozen water, sitting in the dark, waiting. For most of the 20th century, scientists assumed the moon was completely dry. The reasoning was straightforward. The moon has no atmosphere. Without an atmosphere, there is no pressure to keep liquid water on the surface. Any water delivered by comets or asteroids over billions of years would have been exposed directly to the vacuum of space and solar radiation, broken apart by ultraviolet light, and lost. The Apollo missions returned hundreds of pounds of lunar rock and soil. The samples were bone dry. Then, in the 1990s, radar data from spacecraft began hinting at something unusual near the poles. Specifically, in craters near the lunar South Pole, radar signals were bouncing back with a brightness and circular polarization pattern associated with water, ice. In 2009, NASA crashed a small spacecraft called the Lunar Crater Observation and Sensing Satellite into a permanently shadowed crater near the South Pole. The impact plume was analyzed by a second spacecraft flying through it. The result was confirmed. Water ice exists on the moon, real water, frozen in craters where direct sunlight has never reached in billions of years. The amount detected was not trivial. Some estimates based on subsequent orbital mapping suggest there may be hundreds of millions of tons of water ice, distributed across permanently shadowed regions near both poles, with the South Pole containing the larger concentration. This single discovery restructured the entire case for returning humans to the moon. Water in space is not just water. It is oxygen for breathing and hydrogen for rocket fuel when you split its molecules apart. A lunar base with access to water, ice can generate its own propellant. Missions that would otherwise require bringing every pound of fuel from Earth can be resupplied from the surface itself. The moon stops being a destination and becomes a launching point. The South Pole's permanently shadowed craters maintain temperatures around -320 degrees Fahrenheit. That cold is what preserves the ice. But it also makes those craters some of the most challenging places in the solar system to operate. No sunlight means no solar power inside the crater. Temperatures swing violently between the crater interior and the sunlit crater rim. Terrain is uneven, unlit, and unmapped at the resolution needed for a safe landing. That is another reason Artemis 3 will not land at just any site on the moon. The target areas are near the South Pole, specifically selected to balance access to sunlit crater rims for power generation, with proximity to the shadowed regions holding water ice. The exact landing zone for Artemis 3 has been narrowed to a set of candidate sites near a formation called the Shackleton Crater Rim, one of the most precisely studied pieces of real estate in the solar system right now. The Artemis 2 crew cannot visit any of these sites. Their flyby trajectory does not take them over the South Pole. But the mission is gathering baseline data on the moon's surface properties and illumination that will directly inform how South Pole landing sites are approached and documented on future missions. And the data coming back from this crew is arriving faster and in far greater detail than anything previously achieved from lunar distance. Because Artemis 2 is not just testing the spacecraft. It is testing a completely new way of communicating across the vast emptiness between here and the moon. Radio waves travel at the speed of light. Between Earth and the moon, that journey takes about 1.3 seconds each way. It is fast enough that real-time conversation is possible, with only a slight, noticeable delay. Mission control and the crew can talk almost normally. Between Earth and Mars, at average distance, that same signal takes between 3 and 22 minutes each way, depending on where both planets are in their orbits. A question asked from mission control might not receive an answer for 44 minutes. Commands sent to a spacecraft cannot be corrected in real time. Emergencies cannot be managed by a team on Earth the way they can for the moon. The bandwidth problem compounds the delay problem. Traditional radio systems used in spaceflight can transmit data at rates that work reasonably well for the moon, but become severely limiting for Mars. High-definition video, detailed medical imaging, real-time system telemetry from a complex spacecraft. All of that requires far more data capacity than conventional radio provides at interplanetary distances. Artemis 2 is testing a potential solution right now. The spacecraft carries a system called the Orion Artemis 2 Optical Communication System. It uses laser beams rather than radio waves to transmit data between the spacecraft and Earth. The hardware installed on Orion includes a small 4-inch telescope, 2 pointing mechanisms called gimbals that keep the laser locked onto its target, a modem, and control electronics. Laser communications offers advantages that radio cannot match. A laser beam is far more focused than a radio wave, meaning it spreads less over distance and delivers more of its signal energy to the receiving antenna. That concentration translates directly into higher data transmission rates. A laser system the size of the Orion installation can achieve data rates potentially hundreds of times faster than an equivalent radio system, at the same or lower power consumption. The challenge is pointing. A radio antenna can be somewhat imprecise and still function. Because radio waves spread out and fill a wide cone, a laser beam pointed 1 degree off target misses completely. Keeping a 4-inch telescope locked onto a receiving station on Earth, while both the spacecraft and the Earth are moving. across hundreds of thousands of miles of space is an engineering problem that requires extremely precise gimbal control and real-time corrections. Artemis 2 is the first opportunity to test this system at genuine deep space distances with a crewed spacecraft. Earlier optical communication experiments were performed on uncrewed spacecraft and satellites. Having the system run during an operational mission, with crew aboard creating real data demands, heat variations from human activity, vibration from system operations, and electromagnetic noise from life support equipment, tests whether the technology can survive and perform in the actual conditions of a crewed deep space environment. If it works at lunar distance, the next goal is scaling it for Mars. A Mars laser communication link would require larger apertures and higher power transmitters. But the underlying technology and pointing algorithms being validated right now on Artemis 2 are the direct predecessors of any system that would keep a Mars crew connected to Earth. The crew of Artemis 2 is, in a concrete sense, helping build the communications backbone for a mission that will launch years or decades from now. But communication is only part of what makes a Mars mission possible. The other part is understanding what deep space actually does to a human body, and what happens at the cellular level, far beyond the protective shield of Earth's magnetic field, is something no amount of animal testing or computer modeling fully prepared scientists for. At 250 miles altitude, the International Space Station sits inside a bubble. Earth's magnetic field, generated by the planet's iron core, extends outward into space and deflects most high-energy charged particles away from the planet. Astronauts on the station receive roughly 10 times the radiation dose of a person on the ground, which sounds alarming until you compare it to what lies beyond. The moment Orion crossed beyond Earth's magnetic influence on April 2nd, 2026, the 4 astronauts aboard entered an environment with no protective bubble at all. Deep space radiation comes from 2 primary sources. Galactic cosmic rays are high-energy particles, mostly protons and heavier atomic nuclei, accelerated to near light speed by distant stellar explosions and other extreme cosmic events. They arrive from all directions constantly and can penetrate almost any reasonable shielding material. Solar energetic particles are bursts of protons and electrons fired outward by the star at the center of our solar system during solar flares and coronal mass ejections. These are less energetic than galactic cosmic rays, but can arrive in intense sudden bursts. Orion's walls absorb some of this radiation. The metal and composite structure of the spacecraft blocks lower energy particles, but the most energetic cosmic rays pass through the walls almost unimpeded, and when they do, they interact with the material they pass through, including the spacecraft structure itself, creating secondary radiation particles that can be more biologically damaging than the original incoming particle. Inside the human body, this radiation does not feel like anything. There is no heat, no tingling, no flash of pain. It passes through skin, muscle, and organ tissue, occasionally striking DNA molecules and cell nuclei and snapping chemical bonds. Most of the time, the body repairs this damage. Cells have sophisticated DNA repair mechanisms that evolved over billions of years, partly in response to the low-level radiation environment on Earth's surface. But the rate of damage in deep space outpaces what those mechanisms were designed to handle. Over a 10-day mission like Artemis 2, the accumulated dose is insignificant, but within limits NASA has defined as acceptable for career exposure. Over a Mars mission lasting 6 months each way, the cumulative exposure climbs into territory that significantly elevates lifetime cancer risk, and may also affect the central nervous system in ways that are less well understood than the cancer connection. To study this at the cellular level, Artemis 2 carries an experiment called the AVATAR investigation. AVATAR stands for a Virtual Astronaut Tissue Analog Response. The experiment uses organ-on-a-chip devices, tiny engineered structures that replicate the function of human tissues at a miniaturized scale. These chips contain living human cells growing in controlled microenvironments that mimic specific organ conditions. By exposing these chips to the actual deep space radiation environment aboard Orion, rather than simulating that environment in a laboratory on Earth, Scientists can observe how human tissue responds in real time to genuine deep space conditions. Simulated radiation in labs on Earth cannot perfectly replicate the particle spectrum and energy distribution of galactic cosmic rays. The only way to know what those particles do to human cells is to put human cells where those particles actually are. The results from Avatar will directly inform shielding designs, drug countermeasures, and mission duration limits for future crewed missions. Every cellular response logged by that experiment is a data point that could one day protect the crew of the first Mars mission. But radiation is a slow threat, one that accumulates quietly over time. On Artemis 2, the threat that demanded the most immediate engineering attention was far more mundane. The toilet broke. Day 4 of the Artemis 2 mission. The crew has been in space for approximately 3 days. They are roughly 2/3 of the way to the moon. By any measure of human spaceflight history, they are already somewhere extraordinary. The toilet stopped working properly. NASA confirmed the issue during daily mission briefings, describing it as a restoration of the spacecraft's waste management system to normal operations after a malfunction that required troubleshooting. The crew resolved it. The mission continued without interruption to critical objectives. The incident is worth discussing seriously because it reveals something real about where human deep space technology actually stands. The systems that keep 4 people alive in a metal capsule 200,000 miles from Earth are extraordinary achievements of engineering. They are also intricate, interdependent, and subject to the full range of mechanical failure that any complex system faces, including components that were never specifically designed for the gravitational and pressure conditions of deep space. Waste management in spacecraft is genuinely one of the most technically demanding challenges in human spaceflight. There is no gravity to help fluids move in predictable directions. Waste collection systems must use airflow, pressure differentials, and mechanical components to capture material reliably in microgravity. Those systems have moving parts, seals, filters, and sensors, each of which can fail. The Orion spacecraft life support system manages air recycling, carbon dioxide removal, humidity control, temperature regulation, water processing, waste management, and pressurization, all simultaneously, all drawing from finite power supplies, all requiring the crew to monitor and occasionally intervene. NASA designs redundancy into every critical system. If primary carbon dioxide scrubbers fail, backup systems engage. If primary power sources fail, backup power maintains core functions. But redundancy adds weight, and weight in spaceflight is among the most expensive commodities that exists. Every backup system represents a trade-off against other capabilities or fuel. The toilet malfunction on Artemis 2 was a minor system failure on a test flight specifically designed to surface exactly these kinds of problems. That is partly the point of the mission, running the spacecraft with 4 real human beings aboard, in the real deep space environment, generating real heat, real humidity, real biological waste, and consuming real power reveals failure modes that simulations cannot predict. Engineers on the ground monitor all of this data in real time, comparing it to models, flagging anomalies, and updating their understanding of how Orion's systems actually behave with crew aboard. Every anomaly logged on Artemis 2 becomes a design input for Artemis 3. The toilet fix, the timing of that fix, the workaround the crew used, and the exact failure mode will be documented and addressed before the next crew boards Orion. This is not a glamorous part of space exploration. It is the most honest part. The human body requires the same things in deep space that it requires on Earth. It needs air, water, temperature control, and waste management. Delivering those things across hundreds of thousands of miles, inside a sealed capsule with no resupply option and no ability to pull over, demands engineering precision that has no parallel in any other domain. And what that capsule endures physically, not the interior systems but the exterior structure, when it falls back through Earth's atmosphere at 25,000 miles per hour, is something the crew will experience in ways that exceed anything their training could fully prepare them for. The bodies inside the capsule are going to need evaluation the moment it hits the water, and the plan for that evaluation is stranger and more revealing than you might expect. 10 days after launch, Orion will separate from its service module over the Pacific Ocean. The service module the cylindrical section attached to the back of the capsule that carries the main engine, fuel, solar panels, and much of the spacecraft's power generation capacity, gets left behind. It burns up in the atmosphere. The crew capsule alone makes the final plunge. At the moment of re-entry, Orion will be moving at approximately 25,000 miles per hour. For context, a rifle bullet travels at roughly 1,800 miles per hour. Orion enters the atmosphere at nearly 14 times that speed. At that velocity, the air in front of the capsule cannot move out of the way fast enough. It compresses violently, and that compression generates heat. The temperature at the heat shield face reaches approximately 5,000 degrees Fahrenheit. The surface of the shield begins to ablate, the avcoat material burning away in a controlled sacrifice that carries heat away from the capsule. The crew inside does not feel 5,000 degrees. They feel significant G-forces, the physical sensation of deceleration, as the atmosphere slows the capsule from 25,000 miles per hour to roughly 20 miles per hour at parachute deployment. The maximum G-force load during this steeper direct entry profile is higher than it would have been under the original skip re-entry plan. Astronauts under high G-forces feel their bodies become many times heavier. Lifting an arm against several Gs requires conscious effort. Breathing becomes work. The entire atmospheric entry phase lasts only minutes. The parachute sequence begins at high altitude. First, drogue chutes to stabilize and slow the capsule, then the main parachutes to bring it to splashdown speed. Splashdown will occur in the Pacific Ocean, off the coast of San Diego, California, where Navy recovery ships will be waiting. Here is the part that reveals how seriously NASA takes the physical stress of this mission. Immediately after the crew is pulled from the water, they will be taken to a medical facility for evaluation. Then, within hours of splashdown, they will be asked to complete what NASA describes as an obstacle course. The purpose is to measure how quickly their bodies can function under gravity after 10 days in microgravity. When humans spend extended time in zero gravity, the cardiovascular system adapts by reducing the volume of blood it moves, since the heart no longer needs to fight gravity to pump blood to the brain. The muscles in the legs and core, which normally spend much of their energy keeping a person upright against gravity, partially atrophy. The vestibular system, the inner ear mechanism that tells the brain which way is down, becomes confused upon return to gravity. The obstacle course is a timed, documented test of how severely these adaptations have affected the crew's ability to perform physical tasks. Its results will directly inform how the Artemis 3 crew will be evaluated before being cleared for spacewalks on the lunar surface. Where functioning in 1/6 gravity after a multi-day transit from Earth will demand a body that has recovered enough to move safely. If a crew member struggles with a simulated emergency procedure in normal Earth gravity shortly after returning from space, that tells engineers something critical about how much recovery time is needed before a crew can reliably operate on the moon. Artemis 2 is testing the human body as carefully as it is testing the spacecraft. But before any of that happens, the 4 astronauts will spend the busiest, most historically significant hours of their careers doing something that has never been done by any human crew before: flying the far side of the moon. At the deepest point of the Artemis 2 lunar flyby, the spacecraft passes behind the moon. From that position, Earth disappears. The moon's entire bulk sits between Orion and every radio telescope, every tracking antenna, every mission controller staring at their screens in Houston. Every communications link goes silent. Radio waves cannot bend around the moon. There is no relay satellite in position to bridge the gap. For a period of approximately 25 minutes, the 4 astronauts are completely alone. This is called loss of signal, or communications blackout. It happens on every mission that passes behind the moon. It happened on the Apollo missions. Mission control tracks the exact moment signal should disappear and the exact moment it should return, based on precise orbital calculations. If the signal does not return at the predicted time, that silence means something has gone wrong. For the crew, the blackout is not a failure. It is the mission working as designed, but the experience carries a psychological weight that no simulation can replicate. For roughly 25 minutes, every person on Earth who cares about this mission is holding their breath. Inside the capsule, the crew has work to do. The far side of the moon, during those 25 minutes of blackout, and the surrounding approach and departure time is the primary scientific observation window of the entire mission. The astronauts have specific geographic targets assigned to them. Each crew member is positioned at a designated window with a specific camera and a defined list of features to photograph and describe. This is the first time human eyes have observed the far side of the moon at these particular lighting angles and from this particular trajectory. No crew ever passed this close to the far side while it was partially illuminated in this specific way. The far side, in direct human view, is darker looking than the near side. Its surface is covered almost entirely in the pale grey of highland terrain, the ancient, heavily cratered crust that makes up the bulk of the moon's exterior. There are almost none of the dark volcanic plains that give the near side its familiar spotted appearance. Without the dark plains as visual anchors, the far side surface initially looks monotonous, but at low lighting angles, its topography reveals itself in shadow. Crater rims that rise hundreds of feet above the surrounding terrain cast long black lines across the surface. Ridge systems and mountain chains stand out sharply. The density of impact craters becomes visible as a texture, a roughness that tells a geologist this surface has been accumulating hits for billions of years, with very little resurfacing to erase the record. The crew is seeing a geological archive. Everything visible on that surface happened before life appeared on Earth. What they are seeing also includes something that was not visible at all until long-range cameras on approach allowed them to spot it. A massive, dark-floored basin sitting near the south pole of the far side, a place where liquid rock once pooled in an ancient impact scar and then froze into a record that has not changed in roughly 4 billion years. The South Pole Aitken Basin, the largest confirmed impact crater in the entire solar system. And what lies inside it has implications not just for the moon, but for understanding the entire history of the rocky planets. The South Pole Aitken Basin is not visible from Earth. It sits almost entirely on the lunar far side, centered near the South Pole, stretching roughly 1,550 miles across and dropping about 5 miles below the surrounding terrain at its deepest points. To put that in terms of the United States, imagine a single impact scar wide enough to stretch from New York City to Denver, and deep enough that if you placed Mount Everest inside it, the peak would still sit below the rim. This feature formed during the same period of intense bombardment that created the Oriental Basin, but earlier and far more violently. The impacting object is estimated to have been roughly 120 miles in diameter, and it struck with enough force to punch through the lunar crust entirely, exposing material from the moon's deep interior, what scientists call the mantle. That exposed mantle is why the South Pole Aitken Basin matters scientifically beyond its staggering size. The crust of the moon acts like a lid, sealing the interior rocks away from direct observation. Anywhere that lid gets punched through, scientists get a window into what the moon is made of below the surface. The composition of the mantle tells them about how the moon formed, how it differentiated from a molten ball into a layered body with a distinct crust, mantle, and core. Orbital spacecraft have mapped the floor of the basin with spectrometers, instruments that analyze the wavelengths of light reflected off the surface to determine chemical composition. The data shows unusual concentrations of minerals that should only appear if deep crustal or mantle material was excavated and spread across the floor. This is scientific confirmation that the impactor responsible for this feature reached depths that no other impact basin in the solar system has demonstrably penetrated. The South Pole location of this basin is also directly connected to the water ice story, permanently shadowed craters near the lunar South Pole Aitken structure. The specific topography created by this ancient impact, the high crater rims, the deep shadowed floors, the particular pattern of terrain at the lunar South Pole, is what created the cold traps where water ice survived for billions of years. The impactor that created the basin also, indirectly, created the conditions that will make a permanent lunar base possible. Artemis 2 is the first crewed mission to observe this structure from nearby human vantage points under controlled photographic conditions. The crew cannot pass directly over it during their flyby trajectory, but the approach to the far side brings portions of the basin's northern rim into observation range during the period around blackout. What their photographs capture will be combined with existing orbital datasets to build the most detailed composite picture yet of the largest scar in the solar system. But the basin itself is static, a wound from the ancient past. What is happening right now, in the present, above the lunar surface, is something far more dynamic. A layer of charged particles and magnetic anomalies that creates its own invisible weather, and that any future crew spending weeks on the surface will have to survive. Earth is protected. The planet's iron core generates a magnetic field that extends tens of thousands of miles into space, creating a bubble called the magnetosphere. This bubble deflects the constant stream of charged particles flowing outward from the star at the center of our solar system, as well as most galactic cosmic rays. Without it, the surface of Earth would receive radiation doses that would make complex life extremely difficult to sustain. The Moon has no equivalent protection. The Moon had a magnetic field billions of years ago, generated by a molten iron core early in its history. That core has since largely solidified, and the global magnetic field disappeared with it. What remains are scattered magnetic anomalies, regions of the crust that retained remnant magnetism from the early period. But these are local, inconsistent, and far too weak and fragmented to provide anything like the protection Earth's magnetosphere offers. The lunar surface is exposed. Every charged particle streaming outward from the star at the center of our solar system hits the Moon's surface directly, with no deflection. Cosmic rays from deep space arrive unimpeded. During a solar flare or coronal mass ejection, the particle flux at the lunar surface spikes dramatically. For astronauts on the lunar surface, this is a constant hazard. The Apollo crews spent their surface time in short excursions of hours to a few days, and their total accumulated radiation doses were significant, but within what NASA considered acceptable career limits. A crew spending weeks on the surface, as Artemis missions eventually plan, would accumulate doses that demand more active countermeasures. The most practical solution involves shielding. Lunar regolith, the loose soil and fragmented rock covering the surface, is a reasonable radiation absorber in sufficient thickness. A habitat built with regolith piled around and over it would reduce surface radiation exposure significantly. 3 to 6 feet of regolith coverage is estimated to bring the dose rate inside a covered habitat down to roughly the level experienced on the International Space Station. Still elevated compared to Earth's surface, but manageable for extended stays. The South Pole presents one additional advantage beyond water ice. Because of the way the lunar South Pole sits relative to the solar wind, certain locations near the crater rings receive more consistent particle flux data, and the topography of craters provides natural micro-shielding from low-angle particle streams. Future habitat site selection will factor in radiation topography alongside sunlight access and water ice proximity. Artemis 2 is contributing radiation measurements to this dataset in real time. The spacecraft carries dosimeters, devices that measure radiation exposure, which have been running continuously since launch. The data from those instruments, combined with the cellular biology results from the Avatar experiment, will give scientists the most complete picture yet of what the deep space and lunar environment actually delivers to the human body. That picture is essential for what comes next, because the next time humans travel this far from Earth, they will not just fly past, they will slow down. They will enter orbit, and then, for the first time in over 50 years, they will begin the descent. Artemis 3 is currently targeted for late 2028. It will be the first time humans have stood on another world in over half a century, and the operational complexity required to make it happen exceeds that of any previous crewed landing in history, including the Apollo missions. Here is how it works, step by step. Weeks or months before the crew launches from Earth, a lander is sent to lunar orbit on a separate rocket. This lander, either SpaceX's Starship Human Landing System or Blue Origin's Blue Moon, carries enough propellant for a complete lunar descent and ascent. Getting that lander into lunar orbit without a crew is itself a significant operational milestone, one that requires its own successful test flights beforehand. Once the lander is confirmed operational and stable in lunar orbit, the Artemis 3 crew launches from Earth aboard Orion on the Space Launch System rocket. The translunar injection burn sends them on a path to the Moon. Orion enters lunar orbit, a maneuver that requires a braking burn to slow down enough to be captured by the moon's gravity rather than flying past it. This is the first major difference from Artemis 2, which does not enter orbit at all. Once in lunar orbit, Orion rendezvous with the waiting lander. The crew performs a docking maneuver, physically connecting the two spacecraft. Two crew members transfer through the docking port into the lander. The other two remain aboard Orion in lunar orbit. The landing crew closes the hatch, undocks and begins the powered descent. The lander fires its engines to slow down, drop out of orbit, and begin falling toward the surface. The descent covers roughly 60 miles of altitude in a carefully managed burn sequence, transitioning from a near horizontal orbital trajectory to a nearly vertical final approach above the landing site. The final moments of the descent are under partial crew control. Astronauts monitor the landing site from the lander's windows, and the commander can override automated systems if the spacecraft is approaching a hazard the sensors did not detect. This is the same responsibility Neil Armstrong exercised in 1969 when he manually flew the lunar module away from a boulder field and found a safe touchdown point with roughly 30 seconds of fuel remaining. After the surface mission, the crew returns to the lander, performs ascent, enters orbit, and rendezvous with Orion again. This rendezvous, finding and docking with a spacecraft that has been orbiting alone for however long the surface mission lasted, must execute precisely. A failure to dock after ascent leaves the landing crew with no way back to Earth. Each of these steps has never been performed in exactly this configuration before. The landers themselves have not yet completed a crewed test flight. The docking procedures in lunar orbit have not been rehearsed with flight hardware in the actual lunar environment. Artemis 2 is the foundation. Every confirmed data point from this mission builds the case that the next steps are safe to attempt. And the two crew members who will walk on the lunar surface during Artemis 3 will land in one of the most scientifically significant and most hazardous places in the inner solar system. The candidate landing sites for Artemis 3 share one defining characteristic. They are all near permanently shadowed crater rims at the lunar south pole, within reach of water ice deposits. Positioned to access sunlight for power generation, while standing at the edge of craters that have not seen direct sunlight in billions of years. Standing at the rim of one of these craters, a crew member would face a view that has no analogy in human experience. Behind them, a sunlit ridge bathed in constant angled light, the same patch of terrain that has been lit almost continuously for as long as the moon has existed in its current orbital configuration. In front of them, a vertical drop into absolute darkness. The crater floor 300 or more feet below, forever frozen, forever shadowed, holding water from comets that struck a young solar system billions of years before any life existed on Earth. The temperature at the crater rim in sunlight can exceed 250 degrees Fahrenheit. The temperature on the crater floor, just a short distance away, sits permanently near negative 320 degrees Fahrenheit. That is a temperature swing of nearly 600 degrees within a distance a person could throw a rock across. No location on Earth presents that kind of thermal gradient in so small a space. The spacesuits the Artemis 3 crew will wear, the Axiom Space Extravehicular Activity suits contracted by NASA, are designed to operate across this range. They carry their own heating and cooling systems, thermal insulation layers, and reflective outer surfaces. Standing on a sunlit crater rim requires deflecting enormous radiant heat, descending toward the shadowed interior. To collect samples requires generating enough warmth to prevent the suit's mechanical components from seizing in extreme cold. Operating a rover near these sites, which the longer-term Artemis missions plan to do, adds another layer of complexity. Batteries lose capacity drastically at low temperatures. Lubricants that function normally in the warmth of direct sunlight can solidify in shadow. Wheels designed for loose regolith behave differently on the ice and rock mixture at the base of a shadowed crater. And the communication geometry at the South Pole is challenging. The polar angle means the Earth sits low on the horizon from the surface, sometimes barely visible over the terrain. Relay satellites in specific lunar orbits are required to maintain communications from the poles to Earth. Those relay satellites must be in place and functioning before any crewed surface mission in that region can proceed. All of this, the spacesuits, the rovers, the relay satellites, the thermal management, the ice extraction technology, is either in development, in testing, or being planned right now. The 4 astronauts flying past the moon today are not the landing crew. Their mission is to prove the vehicle works, to prove the trajectory is survivable, to prove the systems hold together with human beings inside them at deep space distances. They are doing that right now. In real time, 4 humans, the moon filling their windows, performing the most meticulous test flight in a generation. And what they find when Orion hits the atmosphere on reentry in a few days will either clear the path forward or force NASA to rethink everything again. Before Artemis 2 launched, 4 records had never been broken. No person of color had ever traveled beyond low Earth orbit. No woman had ever traveled beyond low Earth orbit. No non-American had ever flown near the moon. And no crew of 4 had ever reached the deep space distances this mission would cover. All 4 records fell on April 1st, 2026, within hours of each other. Victor Glover is a Navy test pilot, a NASA astronaut who previously served a 6-month rotation aboard the International Space Station. He became the pilot of Artemis 2 after years of training. The moment Orion completed its translunar injection burn and crossed beyond Earth's magnetic influence, Glover became the first person of color in the history of human spaceflight to travel beyond low Earth orbit. 64 years after Yuri Gagarin first left Earth, and 62 years after the Apollo program began sending humans to the moon. That milestone had never previously occurred. Christina Koch is a research engineer and NASA astronaut who holds the record for the longest single spaceflight by a woman, set during her 328-day mission on the International Space Station. She is Artemis 2's mission specialist and the first woman to travel beyond low Earth orbit in history. Women have flown to space since Valentina Tereshkova in 1963. For 63 years after that, no woman had gone farther than Earth orbit. Jeremy Hansen is a Canadian Space Agency astronaut and former Royal Canadian Air Force fighter pilot. He is the first non-American to fly near the moon, placed on this crew through a 2020 treaty between the United States and Canada that formalized Canadian participation in the Artemis program in exchange for crew access. Hansen had never flown to space before this mission. His first spaceflight took him farther from Earth than all but 12 humans in history. Reed Wiseman, the commander, is a Navy test pilot who previously commanded the International Space Station. At 50 years old, he became the oldest person to travel beyond low Earth orbit, a record previously held by astronauts from the Apollo era. These records matter beyond symbolism. They carry a specific engineering significance that is rarely discussed plainly. Space agencies have historically used the demographics of their crews as proxies for the completeness of their life support and equipment design. The Orion spacecraft was explicitly engineered to accommodate a crew of mixed physical dimensions, including specific ergonomic accommodations, suit fitting adjustments, and medical monitoring calibrations tuned for physiological profiles beyond the narrow male demographic that Apollo was designed around. Koch's presence, in particular, drove hardware changes. Suit sizing, workstation positioning, restraint system geometry, and crew interface layouts were evaluated and in some cases adjusted based on the full range of physical dimensions represented by the Artemis 2 crew. That process identified design gaps that would have gone unnoticed with a crew of uniform physical profile. Every future Artemis mission will carry crew members whose safety depends on those adjustments being correct. This mission is, among other things, a validation test for human factors engineering that determines whether Orion is genuinely a spacecraft built for any human being or just one built for a specific kind of human being. The crew already passed one metric when Commander Wiseman radioed Mission Control that all 4 of them were pressed to the windows like children reacting to the moon for the first time. He was describing a crew performing exactly as trained while being moved by something no amount of simulation replicates. That combination, professional precision and genuine human response, is what the mission was built to produce. And yet the mission that set all these records almost did not launch on time, twice, for reasons that exposed a fragility in the program's infrastructure that nobody wanted to talk about publicly. Artemis 2 was supposed to launch in November of 2024, then February of 2026. then March of 2026. It launched April 1st, 2026. The delays stacked up from multiple directions. The heat shield investigation, following Artemis 1, consumed time. Retooling the reentry profile consumed more. But the final delay, the one that pushed the launch from February to March and then from March to April, came from a problem discovered while the rocket was already on the launch pad. A hydrogen leak. The Space Launch System uses liquid hydrogen as one of its primary propellants. Paired with liquid oxygen in the core stage engines, 4 RS-25 engines originally developed for the Space Shuttle program. Liquid hydrogen is stored at -423 degrees Fahrenheit, just 21 degrees above absolute zero, the theoretical temperature at which all molecular motion stops. It is the second coldest liquid in practical engineering use. Handling it requires seals, fittings, and valves that remain pliable and effective at temperatures that cause most materials to become brittle. When a leak was detected in the hydrogen lines during launch preparations, NASA made the decision to roll the entire vehicle back from the launch pad to the Vehicle Assembly Building, the massive structure at Kennedy Space Center where rockets are assembled and prepared. Rolling back a 322-foot rocket to fix a leak is not a quick process. It consumes days, requires re-inspection of systems disturbed by the movement, and restarts the countdown clock from a much earlier position. The decision reflected exactly the engineering culture that kept Apollo alive through multiple crises. A hydrogen leak on the pad is manageable. A hydrogen leak during ascent, near ignition sources, and at velocities where any structural failure becomes catastrophic, is not. The crew was not in the rocket during rollback. They waited. They trained. They ran simulations. And on April 1st, 2026, the Space Launch System lifted off from Launch Pad 39B at Kennedy Space Center at 6:35 in the evening, Eastern Time. The launch was watched by large crowds gathered near the launch site, by astronauts aboard the International Space Station, who photographed the ascending vehicle from orbit, and by people across the world who understood that for the first time in more than 50 years, human beings were leaving Earth orbit. Commander Wiseman radioed his first words from ascent. "We have a beautiful moonrise. We're heading right at it." That is the kind of line that gets remembered. But the technical reality behind those words is what this mission is built on. Every second of the ascent, every burn, every system check in the days that followed, every medical experiment running quietly in the background, all of it feeds forward into the question of what comes next. And what comes next for the Artemis program is a step that has never been taken in this configuration. A step that requires one more piece of the puzzle to be ready. A piece still being assembled right now by two companies in fierce competition to be the first to land humans on the moon in the 21st century. NASA gave one company a contract to land humans on the moon. Then, it gave a contract to a second company to do the same thing. This had never happened before in the history of crewed lunar exploration. Apollo had one lunar module, built by one contractor, Grumman. There was no competition for the final descent. There was no alternative if Grumman's vehicle failed to perform. The decision to fund two competing lander programs simultaneously came from a specific lesson. Single points of failure at the critical moment of a program are catastrophic. If SpaceX's Starship human landing system encounters a development problem that pushes it past the Artemis 3 target date, Blue Origin's Blue Moon system provides a backup that keeps the landing mission on schedule. SpaceX's Starship is, as of 2026, the largest and most powerful rocket ever flown. The full stack, booster and ship combined, stands nearly 400 feet tall. The vehicle is designed to be fully reusable, with both stages returning to land after flight. The version contracted for NASA lunar landings is a modified variant of the upper stage, called the Human Landing System, configured to carry crew from lunar orbit to the surface and back. Starship has completed several successful uncrewed test flights that demonstrated its basic flight capability. The lunar landing variant requires additional development, including a docking port compatible with Orion, life support systems for the crew compartment, and the propellant transfer capability that will allow the vehicle to be refueled in orbit before the crew arrives. Blue Origin's Blue Moon is a purpose-built lunar lander, smaller than Starship, but designed specifically for the mission profile rather than adapted from a larger general-purpose vehicle. Blue Moon has undergone significant ground testing and is progressing through its development milestones as of this writing. Both companies face the same fundamental challenge, proving their vehicle can perform a crewed lunar descent, surface stay, and descent reliably enough that NASA certifies it for human use. That certification process requires uncrewed test flights to the Moon, data review, design refinements, and ultimately a crewed demonstration flight before Artemis 3 crew members board either vehicle for the actual landing. The competition matters for reasons beyond redundancy. It drives both teams to solve problems faster. Each company knows that if they fall behind, the other captures the contract. The pressure of genuine competition, applied to the most demanding engineering challenge in human spaceflight, produces a pace of development that a single sole-source contract historically has not matched. The prize for whichever lander successfully touches down with crew aboard is something beyond a contract value. It is a place in the permanent record of human exploration. The first company to land humans on the Moon in the 21st century will be written into history alongside Grumman. But even the most advanced lander in the world cannot change one fundamental truth about the lunar surface. Getting there is one challenge. Living there long enough to accomplish anything scientifically meaningful is another problem entirely, one that requires infrastructure and technology that does not yet exist and will take the combined effort of multiple nations to build. The Apollo missions were visits. The longest any astronaut spent on the lunar surface during Apollo was 75 hours. The crew of Apollo 17 in December of 1972. They slept in the lunar module, drove a rover across roughly 22 miles of terrain, collected 243 pounds of samples, and came home. The Artemis program is explicitly designed to do something different. Its stated goal is sustainable human presence on the Moon, meaning not just a return visit, but the beginning of a permanent infrastructure. What does that actually require? Power comes first. The lunar day lasts approximately 29 Earth days. During the lunar night, the surface has no sunlight for roughly 2 weeks at a time. The base, relying purely on solar panels, would be powerless for half of every lunar month. The solution near the South Pole exploits a specific geographic feature. Certain crater rims near the South Pole receive sunlight for roughly 90% of the lunar year due to the low angle of the sun relative to the pole. A base positioned on such a rim can maintain near-continuous solar power generation. For the periods of no sunlight, or for operations inside craters, NASA has been developing small nuclear fission reactors designed for lunar surface use. A project called Fission Surface Power has produced a reference design capable of providing tens of kilowatts of continuous power from a reactor about the size of a large trash can, enough to support a small habitat and equipment operation indefinitely, regardless of sunlight conditions. Habitat structures themselves present a unique challenge. The lunar surface has no weather, no erosion, and no atmosphere to carry dust away. But it has micrometeorite bombardment, a constant rain of tiny rock fragments that sandblasts every surface over time. It has extreme thermal cycling between the sunlit and shadow periods. And its regolith carries a static electrical charge that makes dust particles cling aggressively to every surface they contact, including optical systems, mechanical joints, and pressure suit seals. A pressurized habitat on the lunar surface must protect against all of these conditions simultaneously, while maintaining air pressure, temperature control, and radiation shielding for potentially months at a time. The most practical near-term solution uses the same answer as the radiation problem. Pile regolith over it. Thick layers of lunar soil provide thermal mass, micrometeorite protection, and radiation shielding in one measure. The Japan Aerospace Exploration Agency is developing a pressurized lunar rover as part of a formal agreement between Japan and the United States embedded in the Artemis program. This rover, roughly the size of a large recreational vehicle, is designed to support 2 astronauts for up to 30 days of surface travel. It operates with a pressurized interior, meaning astronauts inside can work without spacesuits, dramatically reducing fatigue compared to constantly operating in a pressurized garment. The rover extends the range of human operation far beyond what a spacesuit allows. Apollo crews on foot could travel a few miles from their lander, The pressurized rover extends that range to hundreds of miles over the course of a month-long traverse. That range opens up the possibility of reaching geological targets across a much wider area of the South Pole region, including sections of the South Pole Aitken Basin floor that hold the most scientifically valuable material in the inner solar system. But all of this hardware, the reactors, the habitats, the rovers, the landers, depends on a supply chain that does not yet exist at the moon. And building that supply chain requires solving a problem that sounds simple but carries staggering complexity: keeping humans alive in a place designed to kill them indefinitely, with no resupply from Earth for weeks or months at a time. The International Space Station keeps 8 people alive at roughly 250 miles above Earth. Resupply missions arrive every few months, carrying food, water, equipment, and replacement parts. If something critical fails, a rescue vehicle can reach the station within hours. A lunar base at the South Pole operates under fundamentally different constraints. A resupply mission takes roughly 3 days each way. An emergency evacuation takes days, not hours. There is no cavalry that arrives quickly. Whatever breaks must either be fixed with what is on hand or endured until resupply arrives. This changes the engineering philosophy from redundancy, the idea of having a backup system for every critical function, towards resilience, the ability to maintain core survival functions through improvisation, repair, and resource recovery. Water recovery is the clearest example. On the International Space Station, a system called the Environmental Control and Life Support System recovers approximately 90% of water from all sources, including exhaled breath moisture condensed out of the air, sweat from crew members, and urine processed back into drinkable water through a multi-stage purification process. A lunar base must eventually reach 100% recovery or close to it, supplemented by locally sourced water ice, because there is no practical way to deliver sufficient water for long-term habitation entirely from Earth. The mass required to sustain even a small crew for a year, drinking, cooking, hygiene, and life support, would be enormous at launch costs. Ice mining technology is still in early development. The basic concept involves heating ice-bearing regolith in a sealed chamber, capturing the sublimated water vapor, and condensing it into liquid. The complications involve the fact that the ice in permanently shadowed craters is not pure water. It is mixed with dust, other volatile compounds, and trace chemicals that must be removed before the water is usable. The extraction equipment must operate reliably in the extreme cold of the crater interior, where temperatures approach -300 degrees Fahrenheit, and must be maintainable by crew members wearing pressurized suits in those same temperatures. Food production in space has long been a research goal. Experiments on the International Space Station have demonstrated that certain plants, primarily leafy greens, can be grown in hydroponic systems under artificial light with reasonable yields. A lunar base cannot rely on resupply for food indefinitely, and growing food locally would reduce both the mass that must be launched from Earth and the psychological impact of eating prepackaged food for months at a time. The psychological dimension of long-duration isolation in confined spaces is itself a survival problem. Research from Antarctic stations, submarine deployments, and International Space Station rotations consistently shows that crew cohesion, mental health, and interpersonal dynamics under extended confinement require active management. Mission planners build communication windows with family, recreation time, varied tasks, and regular schedule changes into long-duration mission profiles, specifically because the alternative is crew performance degradation that becomes a safety risk. Artemis 2 is a 10-day mission. Its life support challenges are real but manageable with an existing technology. The toilet problem on day 4 illustrates that even 10 days tests systems beyond what simulation predicts. A 30-day lunar surface mission will surface problems of a different magnitude. And a 6-month Mars mission, which the Artemis architecture is partially designed to enable, will surface problems of a magnitude we have not yet fully imagined. The data being gathered on this flight is the first real step in understanding what those problems actually are. NASA's stated mission for Artemis is returning humans to the moon and establishing sustainable presence there. Every mission planner involved in the program knows that the moon is not the final destination. The deep space life support data gathered on Artemis missions feeds directly into Mars mission planning. The radiation exposure measurements from Artemis 2, combined with the cellular biology from the Avatar experiment, are building the biological dataset that will determine whether a 6-month transit to Mars is survivable with current shielding technology or requires a breakthrough. The free return trajectory mastered on Artemis 2 is the conceptual ancestor of the trajectory architecture for Mars. A crewed Mars mission cannot realistically include a free return option in most scenarios. The distances involved make the energy requirements prohibitive, but the navigation techniques, the deep space communication methods, the human factors data, and the life support engineering all transfer directly. The laser communication system being tested by Artemis 2 is explicitly identified by NASA as a technology stepping stone toward the optical communications infrastructure that a Mars mission would require. At Mars distance, data rates from a conventional radio system become so limiting that high-definition medical imaging, real-time system monitoring, and even regular voice communication become extremely difficult. A laser system scaled up from the Orion installation could maintain functional communication with a Mars crew during portions of the orbital geometry where the planets are close enough to allow it. The fission surface power reactors being developed for the lunar South Pole use the same basic nuclear technology that Mars mission architects have proposed for surface power on Mars. The Moon is the testbed. If a fission reactor can be deployed, operated, and maintained by astronauts on the lunar surface, that validates the same approach for Mars. Even the pressurized rover Japan is building for the Artemis program is directly relevant. Mars missions will require surface mobility over potentially thousands of miles of terrain. A rover that can sustain crew for 30 days without returning to a fixed base is the direct precursor of the vehicles a Mars crew would need. What this means is that the mission currently underway, 4 humans flying past the Moon in a 10-day test flight, is the first physical experiment in a multi-decade program whose true objective is sending humans to another planet. The Moon is the laboratory. Mars is the examination. Every delay, every technical problem, every system anomaly that gets resolved on an Artemis mission is a problem that does not kill someone on the way to Mars. That framing changes how Artemis 2's modest-seeming objectives appear. A flyby that tests life support, radiation exposure, communications, manual piloting, human factors engineering, heat shield performance, and reentry dynamics under real deep space conditions is not a halfway measure. It is the foundation of the most ambitious expansion of human presence in the history of the species, and the 4 crew members currently performing that test are flying with something additional in common with the crew that did it last. The year Apollo 17 launched, the youngest member of the Artemis 2 crew had not yet been born. Gene Cernan stepped off the Moon on December 14, 1972. The 12 people who walked on the Moon during the Apollo program were all born between 1930 and 1944. The youngest among them, Charles, Duke of Apollo 16, was 36 years old when he stood on the lunar surface. He is still alive as of this writing, in his late 80s, old enough to watch Artemis 2 launch and know that humans are near the Moon again for the first time since he left. Every person born after December of 1972 has grown up with the Moon as something humanity visited once and then abandoned. The school textbooks covering human spaceflight end with Apollo, with a list of 12 names and a note that we have not returned. For 53 years, that sentence sat there unchanged. Understanding why that gap happened requires understanding what Apollo actually was and what it was not. Apollo was the most concentrated peacetime engineering effort in human history. At its peak, the program employed over 400,000 people across NASA and its contractors. Its budget in 1966, adjusted for inflation to today's dollars, would be roughly $100 billion per year. It consumed roughly 4% of the entire United States federal budget. It was sustained by a single, specific political motivation: the Cold War. The Soviet Union's demonstrated ability to put satellites and then humans into orbit before the United States represented a perceived geopolitical threat. The Moon race was a proxy military demonstration, showing the world which political system could achieve greater technological feats. When Apollo 11 landed in July of 1969, that demonstration was complete. The race was won, the strategic motivation for maintaining Apollo-level funding evaporated almost immediately. Within 3 years of the first landing, the program was over. What the gap tells us is that humans are capable of extraordinary exploratory achievements when those achievements are backed by extraordinary political will, and that political will, historically, has not been self-sustaining. It requires a driver, competition, inspiration, economic incentive, or crisis. The Artemis program carries a different driver than Apollo. It carries several simultaneously. The confirmed presence of water ice on the moon represents genuine economic and strategic value. Multiple nations, including China, have expressed active intent to establish lunar presence in the coming decades. The development of commercial spaceflight companies willing to invest their own capital in lunar infrastructure introduces an economic engine that was absent during Apollo. Whether these drivers are sufficient to sustain a program across multiple presidential administrations, budget cycles, and generations of engineers is the question that haunts every NASA program manager. The Artemis II crew is flying above that question right now, literally. Their mission's success is the most powerful argument available that the program should continue. And somewhere in the data streaming back from their spacecraft is a number that will either close the door on the next chapter or open it wider than anyone dared predict. Somewhere inside Orion's service module, instruments are measuring the thermal performance of the capsule's systems in real time. And in a few days, the heat shield itself will face its first test, with human lives behind it. The heat shield anomaly from Artemis still does not have a complete explanation. NASA engineers identified contributing factors, including manufacturing variations in the avcoat foam, unexpected turbulent airflow during entry that created localized hotspots, and the interaction between ablation products and the boundary layer of gas forming at the shield surface. But a full mechanistic model, the kind that predicts shield behavior under any entry condition with confidence, has not been publicly declared as achieved. What NASA did was engineer around the uncertainty. By eliminating the skip re-entry, they removed the scenario most sensitive to unpredictable shield behavior. A direct entry profile is more violent but more predictable. The shield takes its maximum thermal load in one continuous event rather than two sequential events, where the first changes the conditions of the second. The sensors embedded in the heat shield during Artemis I detected temperature gradients and erosion patterns at high spatial resolution. Those data points drove the current entry profile design, but the Artemis ice shield performed under uncrewed conditions, without the heat load of human occupants, metabolic activity, and life support systems running inside. The thermal environment inside the capsule is slightly different with crew aboard, and those differences propagate through the vehicle's thermal model in ways that require validation. Artemis II's re-entry will be the most data-rich crewed re-entry in the history of spaceflight. Every sensor embedded in the heat shield, every temperature reading, every pressure measurement on the capsule exterior will be captured and compared against models in real time by teams on the ground who have spent months preparing for this analysis. If the shield performs within predicted parameters, if the erosion patterns match the models, if no unexpected material loss occurs, then NASA will have what it needs to certify the entry profile for Artemis III. The path to lunar orbit opens. If the shield shows unexpected behavior again, the program pauses. Another investigation begins. The Artemis III timeline slips again. The outcome of that re-entry, a matter of minutes of extreme heat and controlled violence over the Pacific Ocean, will determine the schedule of everything that follows. And that re-entry is happening in approximately 4 days from this moment. The crew knows this. Mission Control knows this. Every engineer who has worked on the Orion program for the past decade knows this. 4 people are flying back toward Earth right now, carrying data that nobody on the ground can yet read. In a vehicle whose most critical component has never been tested in exactly these conditions before. That is the tension at the center of this mission. Everything before re-entry is prologue. In April of 1970, 3 astronauts almost died. Jim Lovell, Jack Swigert, and Fred Hayes were 56 hours into their flight to the moon when an oxygen tank in their service module exploded. The explosion crippled the command module, cutting power and eliminating the ability to use the main engine for a normal abort. The lunar module, designed to land 2 people on the moon, became a lifeboat for 3 people trying to stay alive long enough to reach home. What saved them, aside from extraordinary improvisation by crew and ground teams, was physics. Apollo 13 was on a free return trajectory. The moon's gravity curved their path and sent them back toward Earth without any engine burn. They traveled farther from Earth than any humans had in history up to that point, 248,000 miles, a record set under conditions of controlled desperation. They survived. They splashed down on April 17, 1970. The free return trajectory had worked exactly as designed for exactly the crisis scenario it was designed to address. For 56 years, that distance record stood. Artemis II passed it on the outbound leg of its trajectory, confirmed by NASA, reaching a maximum of 252,757 miles from Earth. A new record, set deliberately, set on a mission whose trajectory was explicitly modeled on the one Apollo 13 flew. The parallel is not accidental. Mission architects chose the free return path for Artemis II for the same reason Apollo 13 used it. It is the option that keeps the crew alive if everything goes wrong. The new distance record is a byproduct of that choice, not a goal in itself, but the connection runs deeper than trajectory geometry. The Apollo 13 mission exposed specific failure modes in spacecraft life support, power management, and crew decision-making under extreme stress. The lessons from those 4 days in April of 1970 are woven into the design of Orion, the training of the Artemis II crew, and the procedures sitting in binders at Mission Control in Houston. Lovell, now in his 90s, was alive to watch Artemis II launch. He gave interviews in the days before launch, describing what he felt watching humans prepare to return to the deep space environment he nearly did not survive. The Artemis II crew carries the record that Apollo 13 set not as a burden, but as a credential. They are the first people since that crisis who can say, with data to back it up, that they were farther from home than those 3 men in their failing spacecraft. They also carry a responsibility that extends beyond their own mission. The data they are returning, every system reading, every medical measurement, every observation from the far side of the moon, will inform decisions that will put other crews at risk on future missions. Their diligence is not just personal, it is structural. Every chapter of human spaceflight has been written partly by the chapters that preceded it. Artemis II is the direct inheritor of Apollo 13's most important legacy. The knowledge that the right trajectory chosen in advance can bring people home when everything else fails. What the next chapters of this program will look like depends on decisions that are being made right now, some of them in Houston, some of them in capsule windows, and some of them in the data streaming back from a spacecraft that is already pointing toward home. The crew of Artemis III has not been publicly announced as of this mission. What is known is the selection criteria. The 2 crew members who descend to the lunar surface on Artemis III will include the first woman and the first person of color to stand on the moon. NASA has committed to this publicly. The broader crew of 4 will again represent the international partnerships embedded in the Artemis program structure, including participation from at least 1 international partner agency astronaut. The mission is targeted for no earlier than 2028, contingent on the completion of several prerequisites. The heat shield data from Artemis II's reentry must clear. The selected lander, either SpaceX's Starship human landing system or Blue Origin's Blue Moon, must complete its uncrewed lunar demonstration flight and receive NASA certification for crewed use. The relay satellites needed for South Pole communications must be deployed and confirmed operational. The landing site must be selected from the candidate list and surveyed to the resolution required for safe touchdown. That list of prerequisites is long. Each item on it carries its own schedule risk. The crewed lander demonstration flight alone, a mission that requires flying an uncrewed lander to the moon, descending to the surface, ascending, and returning data sufficient for safety certification, is a major deep space operation in its own right. The Artemis III crew will face a mission profile with more operational steps than any crewed mission in history. The translunar transit, lunar orbit insertion, rendezvous with the waiting lander, docking, crew transfer, lander descent, surface operations at the South Pole, likely lasting several days, lander ascent, rendezvous with the orbiting Orion, docking again, crew transfer back, Lander release. Trans-Earth injection burn. 4 to 5 days of return transit. Re-entry. Splashdown. 14 to 15 distinct critical operations, each of which must succeed for the crew to come home. The crew of Apollo 11 performed roughly the same number of critical steps on their mission. Armstrong and Aldrin spent 2 hours and 30 minutes on the surface. The total time from undocking the lunar module to redocking in lunar orbit was approximately 21 hours. The mission succeeded because every step worked. Artemis III aims to keep the crew on the surface for several days rather than hours. That extended timeline creates more opportunities for equipment issues, suit problems, and unexpected geological conditions to complicate operations. Every lesson from Artemis II feeds into the preparation for that mission. Every system anomaly documented and resolved, every medical data point logged, every re-entry measurement captured becomes part of the engineering foundation on which 14 critical steps must be executed without a single fatal failure. The crew who will take those steps is training right now. They know what the 4 people currently flying past the moon are doing for them. The Apollo program was a national project. It was conceived, funded, and executed by the United States government. As an expression of national capability, the Artemis program is something different. It is a multinational architecture with formal treaty obligations, shared technical contributions, and crew access agreements distributed across more than 20 partner nations. The Artemis Accords are a set of bilateral agreements between the United States and partner nations, establishing norms and principles for lunar exploration. Signatories include Canada, Japan, the European Union member states, Australia, the United Kingdom, the United Arab Emirates, and dozens of other nations. The accords cover data sharing, transparency, interoperability of equipment, and the deconfliction of lunar surface operations to avoid interference between different nations' activities. Canada's contribution, which placed Jeremy Hansen on Artemis II, includes the development of a robotic arm called Canadarm3, the successor to the Canadarm systems that served aboard the Space Shuttle and the International Space Station. Canadarm3 is designed for the Gateway, the small space station planned for lunar orbit that will serve as a waypoint for future Artemis missions. Japan's contribution, the pressurized lunar rover for extended surface operations, represents the largest surface mobility system in the program. Its development also comes with a formal commitment that Japanese astronauts will be among the first people to traverse the lunar surface on future Artemis missions. The European Space Agency contributes the service module for the Orion spacecraft, the cylindrical section that carries the main engine, fuel, and solar panels, and which burns up in Earth's atmosphere on every mission. European engineers built and continue to supply the propulsion and power system that gets the crew to the moon and keeps them alive until re-entry. This distribution of contributions means that a failure in any partner program creates a schedule dependency that no single nation controls. The pressurized rover on schedule matters for Artemis missions beyond the landing. Canadarm3 matters for gateway operations. The European service module matters for every single mission. The multinational architecture is simultaneously the program's greatest strength and a source of significant schedule vulnerability. Its strength is shared cost, shared technical expertise, and shared political commitment. Nations that have formally invested hardware, crew, and treaty obligations in Artemis have a stake in its success that goes beyond any single administration's policy priorities. Its vulnerability is coordination complexity. 20-plus partner agreements, combined with domestic political pressures in each contributing nation, create a web of schedule dependencies that a single nation program does not face. The Artemis II mission, flying right now with one Canadian crew member aboard, represents that multinational commitment in its most human form. Hansen's presence is not symbolic. His assignment to specific observation tasks during the lunar flyby, his shared responsibility for Orion's manual piloting tests, his role in the crew's scientific activities, are all operational contributions to a mission whose success matters to an international coalition. When Orion splashes down off San Diego, the data it carries home will be analyzed by engineers on multiple continents, and those engineers are already planning what comes next, even as the current crew is still in transit. Between the Earth and the Moon, at a specific gravitational balance point that allows an orbiting object to remain stable using minimal fuel. NASA and its partners are planning to build a space station. The Lunar Gateway is not a moon base. It orbits the moon in a particular path called a near rectilinear halo orbit, which brings it as close as about 1,000 miles to the lunar North Pole, and as far as about 45,000 miles from the moon, on the opposite end of its elliptical path. The Gateway completes one orbit of the moon roughly every 7 days. Its purpose is to serve as a waypoint, a refueling and staging point between Earth and the lunar surface. Crew members arriving from Earth aboard Orion can dock with the Gateway, transfer to a lander, descend to the surface, return to the Gateway, and depart for home. The Gateway provides habitation space for extended stays in lunar vicinity, meaning crew members can remain near the moon for weeks or months while landers perform multiple surface sorties. The Gateway also provides a platform for scientific research in the deep space environment, for communications relay to lunar surface operations, and for assembly and staging of larger future missions that would be difficult to prepare in Earth orbit. The first modules of the Gateway are planned for launch in the mid-2020s, with habitation elements following later in the decade. The power and propulsion element, a high-powered solar electric propulsion module, will be the first component launched, providing the Gateway with the ability to maneuver in its halo orbit and maintain position over time. The Gateway's near rectilinear halo orbit was chosen specifically because it is accessible from a wide range of Earth departure trajectories with moderate fuel costs, and because it provides access to both lunar poles, not just the South Pole targeted by early landing missions. As Artemis expands to include operations at multiple lunar locations, the Gateway's position makes it a versatile hub rather than a fixed outpost serving only one region. Artemis missions from Artemis 4 onward are planned to use the Gateway as part of their mission profile. Artemis 2 and 3 do not, because the Gateway will not yet be in place. But the data gathered on Artemis 2, particularly the communications tests, the life support performance, and the human factors measurements, all inform the design specifications for Gateway habitation systems. A station in lunar orbit is not a new idea. It was proposed during the Apollo era and rejected as unnecessary for the specific mission profile of landing flags and footprints on a tight schedule. The decision to build one now reflects the shift from a sprint program to a permanent presence program. You do not build a waypoint station for a one-time visit. The Gateway is infrastructure. Infrastructure implies permanence, and permanence at the moon implies, inevitably, that the moon will cease to be a destination and begin to be a place where people live. The Artemis program does not officially include a permanent crewed lunar base in its published mission architecture. The stated objectives stop at sustainable presence, which means regular human visits and growing surface infrastructure. The trajectory of the program's logic points somewhere beyond that. The combination of the Gateway station in lunar orbit, the pressurized rover for extended surface traverses, fission surface power for continuous energy generation, water, ice extraction for local propellant, and life support, growing habitat infrastructure, and an increasingly capable supply chain from Earth describe something that functions operationally like a base. The distinction between a regularly visited research station and a base where people live is primarily one of duration and continuity, when the first crew spends 30 days on the surface rather than 3 days, living inside a pressurized habitat, driving a pressurized rover across hundreds of miles of South Pole terrain, operating a water extraction system, and maintaining a fission reactor. The word visit no longer quite fits. The first crewed lunar surface stay lasting longer than 30 days will almost certainly happen within this program's timeline, probably within the next 15 to 20 years, if the infrastructure development remains on schedule. The first crew to spend that time on the surface will face a challenge no human has faced, being the first people to sleep in another world more nights than they sleep in their home world during a single assignment. Going to sleep under a lunar sky, with Earth visible as a bright marble in the darkness above, and knowing that the nearest other human beings are hundreds of thousands of miles away in that direction. The psychological reality of genuine long-duration lunar habitation is something research can model, and simulations can approximate, but only experience will fully reveal. Antarctic winter rover crews spend months at the most isolated research stations on Earth. Submarine crews spend months submerged. International Space Station crews spend 6 months in a metal cylinder. All of these environments have produced detailed psychological research that informs habitat design, crew selection, and mission planning. None of them are the moon. The moon is quiet in a way that nothing on Earth is. No atmosphere means no sound from outside. The surface does not move. There is no weather, no season change visible in the sky, no biological variation in the environment. The sensory monotony of long lunar habitation is a real concern in the human factors research, not merely a philosophical one. The Artemis II crew, 10 days from Earth, at the farthest remove any humans have reached in half a century, is already providing data on psychological adaptation, crew cohesion, and behavioral response to the deep space environment that will feed into the planning for much longer missions. When Commander Wiseman described his crew as a bunch of kids who could not get enough of what they were seeing out the window, he was, without intending to, providing one of the most encouraging data points of the mission. Curiosity, sustained under operational pressure, at maximum distance from home, in a capsule that has already had a toilet malfunction and is heading toward the most dangerous re-entry in history, is exactly the crew characteristic that long-duration surface missions will require. The youngest person born before the last humans went to the moon is now in their early 50s. Everyone younger than that has grown up with the moon as something human beings went to once, briefly, and then never returned to. The 53-year gap between Apollo 17 and Artemis II is longer than most people currently alive have been alive. When Artemis II crew members speak from lunar distance, the signal that carries their voices travels the same 2.5-second round-trip path that Apollo astronauts' voices traveled. But the transmission reaches a world with billions of smartphones, global streaming infrastructure, and an internet that did not exist during Apollo. More people are watching this mission in real time, with better imagery and more detailed data publicly available than any previous crewed spaceflight. The crew is aware of this. Mission specialists Koch and Hansen have spoken publicly about their sense of responsibility to the generation that will follow them. The engineers and astronauts currently in school or early career who will build and crew the missions beyond Artemis III. The data gathered on this mission will be published, studied, and referenced in research papers and engineering documents for decades, but the less tangible legacy may matter more. Every child who watched the Space Launch System lift off from Florida on the evening of April 1st, 2026, and understood what they were watching, now has a direct memory of humans leaving Earth orbit for the first time in their lifetime. That memory is the same kind of memory that drove a generation of engineers into aerospace after Apollo. The inspiration is real, and its effects are long delayed. The engineers who will design the first Mars missions are likely already working in aerospace today, some of them on Artemis programs. The astronauts who will crew those missions are probably in their 20s or 30s right now. The technologies they will use are being tested on this mission, and the ones that will follow it. Artemis II is both an end point and a starting point. It is the end of a 53-year absence from the deep space environment. It is the starting point of an expansion of human presence beyond Earth, that if it sustains itself, will not stop at the moon. The 4 humans currently flying back toward Earth are carrying more than data and samples and a camera full of far-side photographs. They are carrying the first physical proof in half a century that humans can reach beyond the protection of Earth's magnetic field and come home. That proof, delivered safely, changes what is possible, not politically, not bureaucratically, but in the most fundamental sense. It removes the 53-year gap as an argument for impossibility. Going back was always physically possible. Artemis II is proving that it is operationally achievable. That is a different and more powerful thing. Right now, the crew of Artemis II is on the return arc of their free return trajectory. They have performed the lunar flyby. They have documented the far side. They have photographed Oriental and observed the edge of the South Pole Aitken Basin. They have run their medical experiments, tested their suits, performed manual piloting checks, eaten their freeze-dried meals, and dealt with a broken toilet. They have spoken to mission control, to their families, and to schools across the world via live downlink events. They have also, by the act of being where they are and coming back, demonstrated something fundamental about the Orion spacecraft and the Space Launch System that no amount of uncrewed testing could prove: that this hardware works with human beings inside it. In approximately 4 days, Orion will complete the return transit, cross back into Earth's gravitational dominance, separate from the service module, and hit the atmosphere at 25,000 miles per hour. For approximately 12 minutes, the spacecraft will be a fireball. Inside that fireball, the crew will be pressed into their seats by deceleration forces that make their bodies feel several times heavier than normal. The noise will be significant. The rattling of the capsule through atmospheric turbulence will be physical. The visual looking out the windows will be fire. Plasma generated by the compressed air ahead of the shield will surround the capsule in a glowing sheath visible from the ground as a streak of light across the Pacific sky. Then the drogue chutes open, then the main chutes, then the water. The Navy recovery ships will reach them within minutes. The crew will be extracted from the capsule. The sensors embedded in the heat shield will have recorded every temperature, every pressure, every ablation measurement during the most important 12 minutes of the program. Those recordings will be downloaded and analyzed before the crew has completed their first medical evaluation. If the shield performed as predicted, Artemis 3 gets its green light. If the shield showed unexpected behavior again, the entire timeline becomes uncertain. The crew does not control that outcome. They did everything correctly. They flew the mission. They ran the tests. They gathered the data. The heat shield will perform how the heat shield performs. That is the honest reality of exploration. You prepare as thoroughly as possible. You build as carefully as you can. And then the physics of the universe either cooperates or it does not. What comes next, whatever it is, will be the most important single data event in the Artemis program since the day Orion splashed down without crew and the engineers discovered the crumbling shield. History is made right now by 4 people in a capsule, by the shield behind which they are sitting, and by the trajectory borrowed from a near disaster over 50 years ago. That is bringing them home whether the engines fire or not. On December 11th, 1972, the crew of Apollo 17 splashed down in the Pacific Ocean. 53 years and 111 days later, 4 astronauts lifted off from the same state, aboard a rocket descended from the same lineage of American heavy lift design, and went back. The arc between those 2 events is not a story of failure. It is a story of what becomes possible when the conditions for exploration are finally assembled correctly. The technology, the international partnerships, the commercial infrastructure, the scientific motivation, and for the first time the economic incentive of water ice waiting in the permanent shadow of lunar crater. Artemis 2 is the first crude chapter of that assembled story. It is 10 days, it is 4 people, it is a flyby, not a landing. And it is, by any honest measure, one of the most significant human spaceflight events in more than half a century. The program it represents extends far beyond this mission. Artemis 3 lands humans on the moon. Artemis 4 and beyond build the South Pole infrastructure. The Gateway Station provides the jumping-off point for extended lunar operations. The pressurized rover from Japan extends human reach across hundreds of miles of terrain that holds 4 billion years of solar system history frozen in its craters. And beyond the moon, the technologies being validated right now carry direct relevance to a mission that will take humans farther from Earth than they have ever gone. 6 months across interplanetary space. 6 months back, a surface that no human foot has touched. A sky where Earth is a pale point of light, indistinguishable from nearby stars. That mission is not scheduled. It does not have a crew. It does not yet have all the technology it requires. But it has a foundation being laid by this program, by these missions, and by the 4 people currently completing the first human deep space journey since the Cold War era ended. Victor Glover, Christina Koch, Jeremy Hansen, Reed Wiseman. They are flying home right now. Their capsule is a small metal cone against the immensity of space, carrying the most complete deep space human performance dataset ever gathered, and heading toward 12 minutes of fire over the Pacific Ocean. What they have proven above everything else, is that human beings can go to deep space, survive there, do meaningful scientific work, break records, see things no eyes have ever seen, and come back to tell the story. That proof was not available 53 years ago, after Apollo 17. It was assumed. It was hoped. It was treated as a foundation for programs that never launched. Now it is data. And data, once gathered, cannot be ungathered. The baseline exists. The first chapter is written. The next crew knows it is achievable because the crew before them achieved it. From here, the program moves forward, or it moves backward. There is no standing still when the moon is already in the window.